So Stirling's approximation. N factorial is approximately equal to the square root of 2 pi n all times n over e to the power n. An a priori probability is an initial probability of value obtained before any additional information is attained. An a posteriori probability is a probability that has been revised using additional information that is later gathered. So, Bayes was a mathematician in like the 1700s, late 1700s. And being a mathematician, he proved this result, which is known as Bayes' theorem. And he thought it was a interesting result. And so, but he didn't think it was anything too important. So he sent this as a remark, as a letter to the editor of a mathematics journal. So it was just like, maybe 100 words or something. So a very small letter to the editor. 200 years later, a statistician, Neyman, was looking through the mathematics and statistics library in the basement of Evans Hall. And I guess he was bored looking through results in the statistics journals. And he happened to be looking at these very old journals in the stacks from the 1700s. And he came upon this result. And he thought to himself, well, this solves everything I wanted. This is like the most important result I've seen since sliced bread. And so since then, Bayesian statistics is probably now the major branch, one of the major branches of statistics. If you look in a catalog in the statistics department, probably 90% of the courses, graduate courses, are in Bayesian statistics, and probably half of the undergraduate courses deal with Bayesian statistics. So it's a major branch of statistics now. So let E1, E2, En be a disjoint, a mutually disjoint partition of the sample space, and let event A be an event of some random experiment, which is a subset of E1 union E2 union En, such that the probability of A is greater than equal to greater than 0. Then the conditional probability of E sub I given A is the following. The probability of E sub I given A is the probability of A given E sub I times the probability of E sub I divided by the sum j equaling 1 to n of the probability of A given E sub j times the probability of E sub j. So let's show this. It's actually a very short, easy proof, basically a one-line proof. So the probability, so notice we want to figure out the probability of E given the E's given A. Maybe we don't know that, but maybe we know A given E. And so notice we've switched around from E given A to A given E. That's Bayes' theorem. We've switched those givens around. So the probability of E given, the probability of E sub I given A is the probability of A and E sub I over the probability of A. Since the E sub I through E sub n was a disjoint, a mutually disjoint partition of the sample space, then the probability of A is the probability j equaling 1 to n of A intersect E sub j. Again, since these are disjoint, mutually disjoint, then the probability of the union j equaling 1 to n of A intersect E sub j, actually maybe these should be all ors, but is the sum j equaling 1 to n of the probability of A and E sub j. Well, the probability of A and E sub I is the probability of A given E sub I times the probability of E sub I. And the probability of A given E sub j is the probability of A given E sub j times the probability of E sub j. And this is Bayes' theorem. So let's do an example. You're given the following tree diagram. I have here A, B, and events E and F. Let's try to make it a little smaller so I can see this. So I want to figure out the probability of A. Well, I just read the tree diagram. The probability of A is 0.4. Oh, actually, I can make it bigger because I actually thought about that. So the probability of A is just 0.4. I want to find the probability of B. Well, the probability of B here is 0.6. I want to figure out the probability of F given A. So I have here probability of F given A is 0.7. I want to figure out the probability of F given B, 0.8. I want to figure out the probability of A and F, 0.4 times 0.7, 0.28. I want to figure out the probability of B and F, 0.6 times 0.8, 0.48. Now, I want to figure out the probability of B given F. I have a B here. I'm given F. I want to figure out the probability of B. It's backwards. I can do it the other way around. I can say, F given B. That's easy. I can figure out what F is given B, but how do you go the other way? Well, Bayes' theorem. So look at everything that involves F. And so, here they are, 28 and 40, 0.28 and 0.48. Add those up, 0.76. That gives you your denominator. So look at everything that involves F here. So everything that involves F, add those all up. That's the denominator. Now the numerator involves both B and F. So now look at B and F. Oh, that's the 0.48. So the answer is 0.48 over 0.46, 12 over 19. And that's Bayes' theorem. So let me do the following. I was reading, this was actually a few years ago, an article in a newspaper, and it was talking about a meeting in Congress, and there was a discussion about whether to test everyone in the United States for the HIV virus test. And their arguments during this meeting, they were giving some numbers, and as I read the article, I was wondering, does anyone notice that all the mathematics that they're talking about is all incorrect? That everything that they're saying, all the conclusions are all wrong, because every statement that they're saying is all incorrect mathematics. So let's go through this. So this is the actual data from the article. So suppose that 0.1% of the population has AIDS. The HIV virus test is 95% accurate with 2% false positive results. So that 95% of those patients with AIDS has a sensitivity of 95% and a specificity of 98%. So that 95% of those patients with AIDS will test positive, and 2% of those patients without AIDS will test positives. If you test positive, what is the probability that you will have AIDS? Everyone in Congress was arguing it was 95%. Well, they weren't arguing. There was no discussion. They just sort of said that. That was their assumption, without argument, without any sort of anyone objecting to what they were saying. Is that you have 95%. It's 95% accurate, therefore 95%. You test and you'll be able to figure out that, well, 95% will have that test positive will have the disease. So let's go through and see what it actually is. 0.1% of the population has the disease. So 0.001 has the disease. 0.95. Oh, and so 0.001 have the disease, therefore 0.999 do not have the disease. 95% of those patients with AIDS will test positive. So 95% of those with the disease will test positive. The remaining 5% will test negative. 2% of those patients without AIDS will test positive. So there's 2% false positive results. So 2% of those people without the disease will test positive. Therefore, 98%, the remaining 98%, will test negative. So let's figure out the probability that if you test positive, you'll actually have the disease. So what's the probability that you have the disease given that you tested positive for the disease? So, well, let's look. We have here positive. So let's look at all the positives. 0.001 times 0.95, 0.00095. 0.999 times 0.02, 0.01998. Add these together, 0.02093. So that's your denominator by Bayes' theorem. The numerator, have the disease and test positive, is 0.00095. So divide that and you get 0.045389393. So if they test you and you test positive, you actually only have a 5% chance that you actually have the disease. It's not 95%, it's 4.5%. So it's much, much less than what they're arguing. And this is always true in any sort of epidemic, that at the beginning of the epidemic, well, even not even epidemic, for any sort of testing that you do, as long as the disease does not have a very high incident rate, as long as your incident rate is like below 50%, your false negatives always swamp your results. So Usually what happens is when you get a test result and it tests positive, usually what they do is they give you then a second test. And so they then give you a different test, usually more invasive, more expensive test, to then see if you have the disease. That then will increase the sensitivity, well, the specificity, and so that you won't have as many problems with these false positives. So these false negatives, sorry. And so so usually until probably you need at least a quarter to half of your population to have the disease before this sort of fact that you're any sort of test gives you lots of false negatives and false positives. So you're overwhelmed by these false positives results. There are 2 identical boxes containing respectively 4 white and 3 red balls, and 3 white and 7 red balls. A box is chosen at random, and a ball is drawn from it. Find the probability that the ball is white. If the ball is white, what is the probability that is from the first box? Okay, so let's do this. So I want to figure out the probability that the ball is white. So let's look at my white balls. Oh, well, let's first do the tree diagram. So I have 2 identical boxes. So each of them have a 1 out of 2 chance of being chosen. I have, for the first box, 4 white and 3 red balls. So 4 white, 3 red balls. So for a total of 7 balls. For the second, I have 3 white and 7 red balls. So 3 white, 7 red balls for a total of 10 balls. Now I want to figure out the probability that the ball is white. So let's look at all the white balls. So 1/2 times 4 over 7, 40 over 140. 3 times 1/2 times 3 tenths, 140, that'll be 21 over 140. Add those, so you get 61 out of 140. Now I want to figure out what's the probability that if the ball is white, so given the ball is white, what's the probability that is from the first box? So let's find the probabilities from the first box, given that the ball is white. So, well, the denominator is what I just calculated, because these are white balls. And let's look at first and white is 40 out of 140. So I get 40 out of 61. There are 4 boys, 2 girls. So 4 boys, 2 girls in room number 1. There are 5 boys, 3 girls in room number 2. A girl from one of the 2 rooms laughed loudly. What is the probability that the girl who laughed loudly is from room 2? So I want to figure out the probability that it is room 2, given that the person who laughed is a girl. So let's look at all the girls. So 1/2 times 1/6, 2 out of 12. 1/2 times 3 over 8, 3 out of 16. And so this is 8 out of 48 plus 9 over 48 is 17 out of 48. And we want the second room. So 9 out of 48 over 17 over 48 is 9 over 17. In Orange County, 51% are males and 49% are females. One adult is selected at random for a survey involving credit card usage. Find the a priori probability that the selected person is a male. It is later learned that the survey subject was smoking a cigar, and 9.5% of males smoke cigars, and only 1.7% of females do. Find probability that the selected subject is male. Okay, so let's do that. So one is an a priori probability, the other is an a posteriori. So let's do that. Oh, and I did that. Okay, wait. I can show it to you. Oops, come on. Yes. There it is. Okay, so let's do this. So make it a little bigger like that. So let M be male, F female, C cigar smoker, N not a cigar smoker. So we're given that 51% of the adults are male. So the probability that the person selected is male is 0.51. Let's do part B. So that's my a priori probability. Next, let's do part B. So we're given that 9.5% of males smoke cigars. So the probability that they smoke cigars, given that they are male, is 0.95. 1.7% of females smoke cigars. So the probability that they smoke cigars, given that the person is a female, is 0.017. So let's figure out the probability that the person is male, given that they smoke a cigar. And so this is just going to be, well, let's figure out the denominator, all the ones with cigars. And so let's multiply these together. 0.95 times 0.51 and multiply these together. 0.49 times 0.017. And I want male and cigar. So 0.95 times 0.51. And so if you do that, you get 0.95 times 0.51 is 0.04845. And then, well, you have the same in denominator. 0.017 times 0.49 is 0.0083. So the denominator is now 0.0567. So if you divide that, you get 0.8532934132. So it changes from 51% to 85%. So this additional information changed your probability. So note that these events must be disjoint, so there's no overlapping, and they have to be exhaustive. So when you're doing your tree diagram, they have to include all the possibilities. And doing that really just sort of says that if you look here, these probabilities should add up always to 1.